Hello, everybody. Today is, day 6, because we skipped around a little bit, but we're looking at single replacement reactions. Single replacement reactions are reactions where you have one uncombined element replace another in a reaction due to the reactivity of it. So we're looking at the examples on pages 20 and the top of page 21, and then the homework relates to the reactions that you saw in the lab portion of the lab. So let's take a look at these examples here. So like I said, with single replacement reactions, really what you have is an uncombined element coming in and taking the place of another. In order for it to do that, it has to have a higher reactivity to take its place. That way it will combine in the reaction and kick the other chemical element, whatever it is, out. So you can see we have a helpful chart to determine this, because if you have something that's more reactive or higher on the metal reactivity chart, then it will kick out something else. So potassium will kick out pretty much anything, but platinum's going to be, the uncombined element for the most part, because it's so low on the reactivity list. Now you notice these are mostly metals here that we're looking at, except for carbon and hydrogen, which are put in there because we do have a lot of carbon and hydrogen style reactions that will occur. So, all right, so let's look at some examples. I have these on the board, and we'll take a closer look at them. All right, first of all, we have potassium reacting with water. So one of the very common reactions that we'll see are based on water reactions. Okay, so we in the past have done a lot of water reactions. We tested calcium and aluminum with water in the lab portion of this. And we can attest that some metals do react with water. Well, how does that work? Well, let's look at potassium and water. So potassium is K, and water I'm going to write as HOH, just because it makes it a little easier to tell what's going on. And what we're trying to, use out of this is in that reactivity chart, is we're trying to see if potassium is higher on that chart than hydrogen is. And it is, of course, because potassium's at the very top and hydrogen's down near the bottom. So what will happen is the potassium will kick out and take the place of that hydrogen. So after the reaction, we end up with a well, it's got to be H2, so we're going to have to balance it because hydrogen can't exist on its own. And you end up with a KOH. Okay, potassium hydroxide. This is a base. So this is very typical of a single replacement reaction where you have a single thing come in, kick out another, and make a new compound out of it. So we have single potassium, and after the reaction, single hydrogen. And this is stuck together over here. Now, to balance it, I had to put that 2 there, so it misbalanced everything because there's 3 hydrogens and there are only 2 before. So one of the tricks is to balance out with a 2 in front of the part that's an odd number. So like there's 1 hydrogen here and 2 there. So it's always going to be odd unless I multiply that by something that would make it even. So we have 2 KOH. That's going to give us 2 potassiums and 4, if you add it up, hydrogens and 2 oxygens. So if we put a 2 in front of the water, that will balance it out. So then we know that this single replacement reaction does generate hydrogen gas. So we can write hydrogen up here. and it makes potassium hydroxide. These are named from the common ion sheet. So if you're confused where I get the names from, that's where that part's coming from. All right, now, as usual for these types of reactions, there's a lot of no reactions. Okay, so one of the things that we see on the chart, the metal reactivity chart, is that hydrogen is above some metals on the chart. But the reality is you really only have the top 4 of those that will react with metal and replace them in a reaction. So barium and nickel both don't do that. Barium, I don't even see it on there. And nickel definitely isn't. So, and you can see that because nickel is in the middle of the periodic table. If you remember the trends of the periodic table, that's a very non-reactive spot. And barium is over here. Well, there's beryllium, there's barium. Barium's quite a long ways down the table. It is in the second column, which is known for reactivity, but this is still what we call a no reaction. Okay, so that's a no reaction. And nickel and water is also a no reaction. All right, we still will write these out though, just for practice. So barium plus water. You can do HOH or H2O, again, the same thing. And abbreviation for no reaction is a NR. So those two are NRs. It's actually quite rare that you'll have a metal and water react with each other, okay? Because that would be terrifying, having rain, rivers, lakes, streams react with any, metals that are around. So that would not be good. All right. Yeah, should we come back to the notes? Doesn't really help much, I don't think. So let's look at the next group of reactions. So metals and acids. Metals and acids are really known to react with each other. It's a very common thing, but still they do need to, be higher on the reactivity chart than hydrogen. That's really what the hydrogen on the metal reactivity chart is for, is to compare with metals for acid-base reactions. So you can see that we have 3 examples here. We have magnesium and hydrochloric acid, we have zinc and phosphoric acid, and we have gold and hydrochloric acid. All right, so first up is magnesium and hydrochloric acid. Now, you won't be able to see this on camera, but the magnesium is pretty high on our list, and the hydrogen and hydrochloric acid is down below lead. So in terms of placement, this is definitely going to react. So how do we figure out what's going on? Well, I like to write it out as a formula equation first. This is known as a word equation. And the formula equation is with the symbols. So magnesium, if we look on the periodic tables at Mg, and hydrochloric acid is a HCl. Okay, now what's trying to happen here is the magnesium is going to be more reactive than the H. So it's going to kick the hydrogen out, much like our reaction earlier with water. So you'll end up with H2. Again, it's got to be H2. It can't just be a hydrogen by itself. And the leftover parts is the magnesium and the chlorine. Now here's kind of a tricky bit. If you remember from doing ionic compounds before, there are charges associated with the the positive cations and the negative anions. So the way that works is Mg is a 2 plus and Cl is a 1 negative. So when those go together, you actually need 2 chlorines to balance out the charge of the magnesium. So it's going to be MgCl2. Okay, which means to balance it, there needs to be a 2 on the HCl over here, like that. Okay, so that's the reaction. To describe that in words, because we do have to finish out the word equation up here, this is hydrogen, and that's magnesium chloride. Okay, again, these are coming from the ion sheet, except for hydrogen. Hydrogen is the just hydrogen. Hydrogen plus magnesium, and that's chloride. You do want to be careful because there's chlorate, there's hypochlorate, there's all kinds of different chloride ions, so you want to make sure that you're keeping them straight. All right, next up is zinc. So is zinc reactive enough to displace a hydrogen on an acid? And again, you want to look at your reference guide for this. It came out kind of fuzzy on mine, but zinc is well above hydrogen. There's zinc, and then it's iron, tin, lead, and then hydrogen. So zinc will react. Gold won't. Gold is at the very bottom of the list. So we could save ourselves a little work right now and just say that number 6 is a no reaction, or NR here. Because gold, let's just get this down here, gold, Au, and hydrochloric acid just don't do anything, okay? Which is why we like to make jewelry out of gold, because it's not reactive with pretty much anything. So it will stick around and it won't leave like weird bands on your skin and stuff from exposure to the elements and stuff. All right, but we do know zinc reacts, and let's lay this out here. So we have zinc and phosphoric acid. That might be H3PO4. It is H3PO4. One of the things that we skipped over at detriment to our intelligence is naming acids. So phosphoric, you really need to know hydrochloric, phosphoric, and sulfuric. Those are the big ones. All right, so the zinc kicks out the hydrogen. We got a lot of weird stuff going on here, and we'll talk about what's going on. But the zinc does replace the hydrogen, and that means for us that after the reaction, you're going to have hydrogen gas, and then you're going to have the zinc in where the H3 was previously. In order for this to work, we do need to look at the charges of the ions. And the reason this is H3 is because PO4 is a special 3 negative, and zinc is a 2 plus charge. So that's that combination where you have a 2 plus and a 3 negative, and you got to have a common multiple of a 6. So we actually need 3 zincs. And you got to put parentheses around the PO4 with a 2 on the outside. So it's ZN3 PO4. Okay. for the ions, switching the crisscrossing the charges and all that. Obviously not the prettiest looking thing ever, but that does mean that we need to put a 2 in front of the H3PO4 to get the 2 phosphates that we have over here with the parentheses. We need a 3 in front of our zinc. And now we need 2 times 3 is 6. We need 3 times 2 here, 6 hydrogens. So that's our balanced reaction. So what does this make? Well, it makes hydrogen and it makes zinc phosphate. So those are the 2 parts that are created out of that reaction. All right, so the last bit that we have to look at are the, oops, where did I put it? Yeah. Are the metal plus ionic compounds. So I have those here now. So we have, so these reactions are all going to be a metal trying to beat out another one in a fight. So this is a comparison between metals, okay? So is iron more reactive than copper? On our chart, yes, iron is higher on the list than copper is, okay? Is copper more reactive than iron? Well, it can't be, right? Because we just said that in this case, it was more reactive. So let's do that first. Let's mark the non-reactive one. So this one would be a no reaction. Okay. What about tin and sodium nitrate? Tin is really low on our list, and sodium is right towards the top. So this reaction would also not work, okay, because of the where they are on our helpful chart here. Okay, so these 2 right off the bat we know shouldn't react. There should be no reactions. So let's look at how a metal and a metal and a metal react with each other in the first example. So if we have iron here, which is a Fe, and copper sulfate. So we do need our ion sheet, to try to double check what's going on with the reaction. And sulfate is a SO4 2 negative. And copper here is Cu2 plus. So the 2 plus and the 2 negative go together perfectly, and we end up with a CuSO4. After the reaction, this is going to be really important though, because the iron is taking the place of the copper. As we mentioned, this is a reaction that happens. The iron is more reactive than the copper, so it's going to kick it out. Copper is going to be on its own. Let's write that down. But the iron's going to take its place. The iron is a 3 plus, where the copper was only a 2 plus. So now the charges aren't going to be balanced anymore. It was a 2 plus 2 negative. Now it's going to be a 3 plus 2 negative. So we got to get 6 happening on that formula. So it's going to be a Fe2, parentheses around it, SO4, 3 will be the product. So it goes iron, copper sulfate to copper, iron sulfate is what's happening. So on this side, we're going to say copper plus, and I don't have room for this, we'll write up here, iron sulfate. Technically, it probably has to be iron 3 sulfate, but that's close enough here for us. Balancing, we have 3 of the sulfates, so we got to get 3 on this side. That gets 3 coppers for us, so you have to balance with 3 coppers on this side. So you end up with a, 2, whoops, I almost forgot the 2 on the iron. So you have 2 Fe, 3 copper, 2 sulfates, 3 coppers, and 1 iron 3 sulfate. Okay, so that's that's the general idea. Let's look at the last one that actually does react down here at the bottom. Sorry about the camera angles. So we have zinc and the lead-2 acetate. Lead-2 acetate is a huge compound. That's going to be fun to write. Zinc is easy. Zinc is just Zn. Oh, we didn't talk about this one. The zinc is way above lead on the reactivity chart. We have zinc right underneath the carbon there, and lead is down below tin. So the zinc will kick the lead out of the lead-2 acetate. All right, lead. Lead is Pb, and it's got a charge of 2, C2H3. Acetate's huge. It's C2H3O2. I have parentheses around that because the lead has a 2 charge. So we have 2 of the acetates. Acetates are a -1. Let me write that up here. C2H3O2 is a 1 negative. Lead is a 2 plus. Now you're probably wondering, now that I'm thinking about it, why don't you have the charges on the metals when they're by themselves? Okay, how come the charge only shows up later when it's combined in the compound? And that's because the charges are developed by making the compound. This is zinc metal, meaning that it has not been reacted. It's just a big chunk of zinc metal, and that's all that it is. This lead has been reacted by the acetate and therefore has a charge. But because the zinc is more reactive than the lead, after the reaction, the lead is the metal that's just hanging out, and thus does not have a charge. But the zinc takes the place of the lead in the acetate, and that does make it have a charge. And zinc has the same charge actually as lead. It's a 2 plus. So this is a nice even switch where there's still parentheses around the acetate and there's a 2 on the outside. So this equation actually does balance itself nicely. Okay, so for the word equation, we're looking at lead and zinc acetate. And there you go. That's how that reaction would work. It makes lead and zinc acetate. So again, just to back up, we looked at 3 different types of reactions here with our synthesis reactions. We looked at metal and water, which they have to be the top 4 in order to react with water. Top 5 on our chart actually, because sorry, top 5 on the chart. Okay, for metal and water. Metal and acid, they have to be above the hydrogen in our reactivity series. And then we just saw how metals can displace other metals in ionic compounds as long as they're above the other metal in the metal reactivity series. Okay, so that's how single replacement reactions work. They're basically controlled by how reactive things are. And I hope you can use that information to help you figure it out.